Okay, so we want to look at how we can do locally linear approximations today. This is a method to where we're going to use the tangent line at a point to approximate what the output of the function would be at a point near that point of tangency. Okay, so if you consider what a tangent line would look like, I have just a graph of a generic function here. You can see that at the point x, the tangent line is very close to the curve itself, right? So the idea being, if you take some point, I just called it A, which is close to x, and you found the point on the tangent line at A, it's a good approximation for the actual point on the curve. Okay, so we would use this in a case where maybe you don't know the function, you only know its slope, and you only know the point of tangency, so all you have is the tangent line. It could be a case where you don't have a calculator available and it's just too difficult or too much of a headache, or it could be that your teacher asked you a question to use a locally linear approximation. That's probably the first place you're going to use it. It is in class. But so, and really with this, it's really just a glorified tangent line equation. If you do look in the textbook, the equation they have is equivalent to this. Their notation, I think, is not very nice. It's really kind of confusing. You might hit that too if you ask for help on the My Math Lab. It's probably going to give you the same stuff. It just is not very pleasant looking. It does match up, just it makes it look confusing. So what I would recommend is a process, and we'll do one together here. And again, we can use the tangent line to approximate f of a if a is sufficiently close to x. Right? Well, that would be the tangent line at x. I guess I should put that. So what we can do, though, is really to get the linear approximation equation, this L of x equals, what we're going to do is just take our standard point slope form of a line. Okay? We're going to use our point of tangency to fill in x sub 1 and y sub 1 like we always do. We're going to find the derivative, find our slope, put x or maybe y if we need to into that to find what we get. And then we're going to put this, so we'll have y equals some value, x minus some value, plus a value. So it's nice to just move y sub 1 over here. And then for the locally linear approximation, we just replace y with capital L of x to stand for that locally linear approximation. And the idea being that, we're going to get, we can approximate that based on that. And we also talked about, good to know is that, like in this case, we can see that the original function f of x is concave up, right? So the tangent line will lie underneath it. That means that this approximation, if we use it from the tangent line here, this locally linear approximation is going to be a bit of an underestimate. It's going to be lower. Okay. The same thing, though, if you consider a tangent line where it's concave down, we can see that a point on the tangent line would be an overestimate. Okay. I have trouble keeping them straight, so I usually have to draw a picture. But that's not the worst thing in the world, right? That's why papers have margins, I guess, so we can draw pictures. So let's go ahead and take a look at an example here. So just a nice cubic function here. All right, so example 1 here, f of x equals 3x cubed minus 7x squared plus 5. We want to find what is the estimate for f of 1.01 using the local linear approximation for f at 1. So this is a case where could we take the time to put 1.01 in here and actually find what f of 1.01 is?
Yeah.
Do we want to? No, we don't want to. So we're going to do a local linear approximation. We're going to figure out what the tangent line that hits that graph is at 1 and then use that line to approximate what f of 1.01 would be. And we get pretty close to this, actually. And then we're going to ask, is it an over or under approximation? Using calculus, like obviously you could type it in your calculator and tell, but we want to say, we're talking about concave up, concave down. So we'll get to that. So our first step is for this function, we know if x is 1, we have to find the point of tangency. So I'm going to take and do f of 1, 3 times 1 cubed, minus 7 times 1 squared, plus 5. So that's 3 plus 5, is that 1? So our point of tangency is the ordered pair 1, 1. Right? And then we just need to find the slope. So to find the slope, we're going to need to find the first derivative. Now it's a nice function that we can find the derivative of without too much trouble. So f prime of x is 9x squared minus 14x. Okay, to find the slope, we will get f prime of 1 is 9 times 1 squared minus 14 times 1. So f prime of 1 would be negative 5. So that tells us that our slope for our tangent line would be negative 5. And we're going to use that to write our L of x equals, right? It's a glorified tangent line. That's all we have here. So what we'll get at this point is y minus 1 equals negative 5, x minus 1. I mean, this 1 went here. They're both 1s, so it's not really that interesting. Let's go ahead and move the 1 over. So negative 5, x minus 1 plus 1. I would not distribute the negative 5. What you'll find is if we're going to have to plug in and do some arithmetic by hand, it's going to be a lot easier to do 1.01 minus 1 than it is going to be to multiply 1.01 times 5 and all that other stuff. So, now at this point, our local linear approximation would be L of x equals negative 5, x minus 1 plus 1. So there's the approximation equation. If we want to approximate now f of 1.01, that's going to be approximately equal to L of 1.01. True? Does that seem right? All right, so to do that one, then we get negative 5, 1.01 minus 1 plus 1. Well, that's negative 5 times 0.01 plus 1. So that's going to be negative 0.05 plus 1. So we'll get f of 1.01 is approximately 0.95 would be our approximation. Does that look reasonable to everybody? Okay, so that's our approximation. That's our estimate for f of 1.01 using the local linear approximation for f at 1. Okay. The next question would be, is it an over or under approximation? Well, to do that, we need to know if it's concave up or concave down. Okay. To know if it's concave up or concave down, we have to look at the second derivative. So and see what's going on at 1. So for the second derivative, the first derivative was right here. It was 9x squared minus 14x. So this would be 18x minus 14. You could do a number line. We don't need to. We only care about one value. We only care at 1, what it is. Like it could be concave up, concave down, wherever. We just care what's happening at 1. So let's do f double prime of 1, which would be 4, right? 18 minus 14. So f double prime of 1 is greater than 0. Therefore, it's concave up, right? And again, I told you I'd never remember this. I'm going to draw a little picture, draw a tangent line. Well, that tangent line's below the curve, correct? So since it's below the curve, it's going to be an under approximation. I don't remember the number. I might have it on my calculator still. Okay, if we actually, just to check our work, right? If we actually plug 1.01 into this function, right? If I actually calculate the true value of it, the actual value was 0.950203. So we see that our value was really close, right? 3 decimal places, but it actually was a bit of an under approximation. Does that follow for everybody? Does that seem okay? All right. Okay, let's go ahead and look at this next one. This is from the worksheet that's linked on the agenda here. So let f be a function with f of 2 equals negative 2. So let's read through it. Such that for all points x, y on the graph of f, the slope is given by x squared minus 1 over 2y. Write an equation for the tangent line to the graph of f at x equals 2 and use it to approximate f of 2.2. So, a lot of words, right? Way more words than I would like to ever see. But what's this telling us? Let f be a function with f of 2 equals negative 2. Well, that just means the ordered pair 2, negative 2, that's our point of tangency, right? It talks about at that point later. So that's a good thing to know. And then this whole such that for all points x, y on the graph of f, the slope is given by this. It's because you could have some discontinuity issues, which that's not really anything that we do a ton of, right? But sometimes it's just good, they're just being thorough. On the graph of f, the slope is given by x squared minus 1 over 2y. So if we know a point, that's going to give us the slope. If we know a point of tangency and the slope, we have a tangent line equation, which we're going to use for our approximation. So let's see what we get here. So again, we said that our point of tangency is going to be at 2, negative 2, right? And then we know that our slope is going to be, it's going to be m equals x squared minus y over 2y. And we'll just plug in the 2 and the negative 2 for x and y, respectively. So that's 2 squared minus 1, 2 times negative 2, and that's negative 3/4. Okay. So then the equation of our tangent line, now it's kind of interesting. We don't know anything about the original function other than what its derivative is and one point on it. Right? So this is a case where you have to do it this way. This is all that we know. We have to do the best that we can. Which a lot of times you might have a case like this where you just know certain points and you want to kind of extrapolate values at other points. Would be a good way to do. This would be a great way to do that. And so with this, we get y plus 2 equals negative 3/4 x minus 2. Again, it was y minus negative 2 is why we got the y plus 2. I'm going to move the things over, or the 2 over. So negative 3/4 x minus 2 minus 2. And that's our linearization equation, our locally linear equation. Negative 3/4 x minus 2 minus 2. So now with this, we want to be able to do this approximation now. To approximate, so f of 2.2, again, is approximately L of 2.2. Right? We know it's not going to be the exact value because we don't know the function, but we know that this will give us a good approximation. So with this, we get negative 3, 2.2 minus 2 minus 2. And here I would really focus on maybe using some fractions here. So you subtract this, you get 0.2, which is 2 over 10, which is 1 over 5. So we get negative 3/4 times 1/5 minus 2, which gives us negative 3 over 20 minus 2. So that gives us that it's approximately negative 2 3/20. Right? Or you could write it as negative 43/20. Those are both correct. So that's the process here. Right now, some of the other questions ask about overestimate or underestimate. We don't have enough information here because we don't know about the concavity and the function of 2. We have no idea. Okay, so that's a general idea. So just for the weekend, maybe try to finish the rest of these, take a look at them, and on Monday we'll discuss them.